There is a feeling amongst some people that science is a subject. It's something that you do between 9 and 10, 3 days a week. It's a class that you had to pass in high school. It's a topic. They have books devoted to it. It's complete garbage. Science is not a subject. Science is a method. It's just simply a way of asking the right question. That's all science is. Answering a question that gives you an answer that you can kind of understand. And where am I on the screen? Chemistry fits into this. With this great little definition that chemistry is the scientific study of matter. And that's nice. It's only 1, 2, 3, 4, 5, 6, 7 words. It's a good, nice little self-contained definition. But we don't know what that word means, and we don't know what that word means. Okay, so we're going to do two things in the first week. We're going to elaborate on this nice, warm, soft, and fuzzy topic that we can discuss and debate, and then this fact. Facts live here. So, science is a method of observation that generates testable data. What did I write in my notes? Science is a method of observation that results in testable theories. Same thing. Okay. That is the important word. And we'll elucidate on that in a minute. And then matter. You don't know what matter is?
Physical material.
Yeah. Matter basically is anything that has mass or occupies space. And if it does either of those, then it can be measured. It can be observed, it can be measured, sometimes directly, sometimes indirectly. But it's real. It's manifested, it's actually there. Okay, so we'll spend the first chapter talking a little bit about that, which is, again, fuzzy kind of topic. And then we've got to talk all about this. And that's going to lead us into measurement and how we're going to go about measuring. So let's talk about science. The scientific method is really fundamentally simple. Starts with observation. This is one of the things that you have to be intellectually honest and rigorous with yourself, because the observation is going to lead, perhaps, if you collect more data, to a trend. You might be able to see, if it's mathematical data, you might be able to see a trend on a chart. And then that trend will, because we all have curious human brains, will lead to a theory about what it is that the observations and the data are actually doing. Either what they're doing or where they come from. And then we have to invent a test to determine, ladies and gentlemen, if you have yet to meet Miss Joyce, this is Miss Joyce. No. There's never a better time to introduce her. If you're ever in doubt of what am I supposed to be doing in chemistry, this fine
Yes.
lady right
For
here
those of you,
will
and I don't
set you
see
straight.
anybody in here that has been in here before, I am the lab manager. I'm also the general dog's buddy. I do just about anything.
She's chemistry mom.
But, yeah, or grandmother, whichever you, but if you need anything, my office number is 106. It's just around the corner from the help desk. Okay? My cell phone number is 940-224-9674. You may understand, or you may think you're understanding what Dr. McGuire is telling you in class. And you think, oh, that's good, I've got it, not a problem. And then you get home and you get everything done and you sit down and you start to study and you think, what did he say? Because it's gone away and it's dark and you don't know what to do. That's when you text me, tell me who you are. That way I'll know who I'm talking to. And I will ask me your question and I'll text you back. I won't give you the answer, but I will help explain something or I will send you where you can find it, okay? And I do answer the phone, I promise. It's not just, I don't ignore it, I will answer you, and it's not a big deal, okay? So, for those of you that are in lab today, lab is in here. You don't have to worry about what you've got on or anything else. Today is the first day, it's hello, how are you? This is me, this is you. You know, just kind of get to know, do a little safety stuff, and that's all lab will be for this whole week. So, but it is going to be in here.
I thought I didn't bring them.
Ah,
I have a
got
magic,
it.
I have a
Well, I
magic
probably
touch
have it.
later on.
I probably have a deck. I also have dominoes back there. So, but anyway, sorry to interrupt. I just wanted,
No.
I looked up and was like, oh, he's already started. So, if you have any questions, come and see me. Okay? And I always have chocolate by the door, so. But,
You have to start here, okay? Your observations might lead you to a trend, which might generate in your mind a theory, and then you've got to come up with a test. And there's no point in this test if the test can generate thousands of different possible answers. You want that test to give you a yes or a no, those are the best, or a number. Good numbers would be a 1 or a 0. That's a yes it is or no it isn't. Or in some branches of physics, a +1 or a -1. Okay. That's the real hard part right here. But what we've got to do, I said, we've got to be intellectually honest with ourselves. You cannot start with the theory and then go look for stuff that supports your idea. Because that's going to just lead you to be able to cherry pick. Well, you know, I think I want to prove a certain thing. Let me just go and find something that supports my argument. And what we're going to prove today is that supporting your argument is worthless. It's not what we do. It is not what science is about. Coming up with a theory and then having boundless amounts of information that support that theory is worthless. You know what you need? You need one piece of information that says, you're wrong. That's what you need. So all of this relies on a couple of buzzwords. So we keep ourselves honest to ourselves. By two things that are interwoven, and they are peer review and reproducibility. So, what if I said I can turn lead into gold, something that the middle-aged chemists used to want to try to do. If you give me a lump of lead, I can turn that into gold. That would be interesting. That would be newsworthy. And you give me the piece of lead, and I leave the room, and I come back with a piece of gold. You give me another piece of lead, and I leave the room. Actually, it'd be more worthwhile for me to turn the gold into lead. That would be economically useful for me. But it appears to everybody concerned, and you're getting gold out of this, so you're happy, and you're not really going to question it. But I'm not going to tell you how I do it. I'm not going to reveal to the world how it's done. And there is an argument. There's a famous atheist. You shouldn't start day one, hour one of your Concordia education by talking about Christopher Hitchens, but very, very famous atheist who said along the lines of, if your theory doesn't come with a supporting argument, then I'm going to spend about the same amount of time dismissing it as you are defending it, which is none. Okay? If you don't come to me with any evidence, then I don't have to hear your arguments. I don't. Which is why science solves problems really well. And then it just opts not to solve some questions at all because they fall outside of the realm of what we do. And you can go and go to philosophy class and go and debate that. It's not what we're up to. We're talking about evidence. So what's your name?
Deirdre.
If I shared my secret in a written paper with Deirdre, so now that she can read it and go, oh, that kind of looks like it might happen, and then she goes off to the lab and reproduces my work, it can move forward. But until we do those, your theory is just a theory. You don't keep it to yourself. You want to share it with the world. And we share stuff with the world, guess what? For free. There's a living to be made out of this, but you have to give your science away. If you can make money out of it, you have the option of patenting it or copyrighting it, but that's all covered under the intellectual property law right here. That if you're the first person to print it, then you get to hold on to the patent. But unless this happens, we can just dismiss you. What was I going to do next? So all of this collectively, all of this collective, all information collectively builds. Oh, I just split an infinitive. Collectively builds to something that we call a paradigm. And a paradigm is the best available current explanation. And paradigms are wonderful things because they're not carved in stone. They're written on paper. paradigms are the best available explanation. Newton observes gravity, supposedly by watching an apple fall from a tree, maybe, maybe not, and writes a mathematical equation that describes gravity that still works to this day, 400 years later. Wonderful piece of observation, testable theory, then takes objects into the lab and drops them and realizes that heavy masses and light masses all fall at the same acceleration, quantifies it, puts it all together in a nice package. That now becomes part of our paradigm. And then 1918, something like that, 1920, Einstein comes along and demolishes it. We still keep the Newton stuff because it works on a big scale, but Einstein adds something completely foreign and unusual that nobody had expected, that light gets bent. Nobody was expecting that. We figured that light traveled in straight lines. Again, Newton tells us all of that stuff. So when the new stuff comes along, it just collectively builds. And there are times when that paradigm mutates into something new. We just adopt the new piece of information and tag it on. There are times when it completely smashes what we had before, and we call that a shift. So we've got two things we're going to talk about right here. Paradigm shift is an abrupt change in understanding. And we went through a bunch of those at the beginning of the last century. Atomic physics. This was a completely new theory with a completely new branch of mathematics. People just weren't ready for that. And so that is a complete fundamental shift in our understanding of how the world works. And then sometimes, those are bullet points. The paradigm just falls flat. Here's an example of, I'm not going to tell you what it is. Quiz number 1. Day 1. Wasn't ready for a quiz on day 1. Which of these is a berry? Keep going, I'm not done yet. Is it a strawberry? Then there might be more than one correct answer. Is it a strawberry? Is it a raspberry? Is it a blackberry? Or is it a banana?
It's a banana.
It's the banana. And only the banana. Because strawberries are not berries, and raspberries are not berries, and blackberries are not berries. This is a case, and does anybody of us care? Does anybody care? No, not really. This is an example of we have moved on, we completely understand what a berry is, and none of us care enough to change our behavior because this is not important enough. Do you know why? Were you going to say that the banana is a berry?
Yeah.
Why?
Because the strawberry, the raspberry, and blackberry, they all come from plants that grow multiple fruits. So they come from like agave plants or something like that.
What were you going to say?
I just know random facts.
Yeah, like most pandas are left-handed.
Did not know that, but
Yeah.
cannot wait to talk about
The definition of a berry is a fruit in which the seeds are evenly distributed amongst the meat of the fruit, which is true of the seeds inside a banana. They're scattered throughout the fruit. In strawberries and raspberries and blackberries, the seeds are on the outside. Therefore, they cannot be berries. Fun fact. Anybody think of a paradigm then that falls into one of these two categories? Something useful, either that we just don't care about enough to change, or something that happened that was severe enough for us to completely change our worldview.
I don't know if it's that major, but the unadoption of Pluto from being a planet.
Pluto is not a planet. Anybody watch Rick and Morty? Yeah, Pluto was a planet for 50 years, and is no longer a planet. There are other planets, maybe, that don't orbit in the same plane as our solar system. They're on a different plane going around the sun. They're a bit further out, and they're difficult to see. So we might find some more, and then dismiss those as well.
The way the model of the atoms changed over the years.
So what happened at the turn, like in the 1910s, 1920s, is we started observing subatomic particles. We thought, previously to that, this goes way back to the Greeks, we had thought previous to that the atom was the smallest indivisible particle. And that is the textbook definition that you will learn in this class. An atom is the smallest indivisible particle. And then we will take a breath, and it will tell you all of the things that are inside an atom. Because it's not anymore. We now understand that there are protons, neutrons, and electrons inside that, and those are made of quarks, some of which are ups and some of which are downs. Don't ask. And that they behave, you all know what a wave is, right? And you may have done high school chemistry and high school physics, and you might think you understand what a wave of energy is. Well, an electron is a wave of probability. And yeah, go with that. Because that's about as difficult to understand 100 years after it was first proposed as it was then. Like, nobody understood it then, and nobody understands it now. That's a region where, you know, if you want to go and die for it, we will let you go die for it. Anything else? Because I think I was going to set that as a homework question. And then Blackboard was locked. I might still. Questions like that come with a participation grade because there is no real wrong answer. Who's the greatest scientific mind of all time? There is no correct answer. Anything that I said, like along those lines, would be up for grabs. There is a correct answer. It's Isaac Newton. Okay, so we have all of that. Which order do I want to put this in?
Will you email us when Blackboard's up?
As soon as we're done here, well, we've got to go to chapel, but then I'm going to track down the guy who will unlock my Blackboard for me, and it will be done before, I'm hoping, before 11. So observations build into theories, and they are only as good as the quality of the data. We have two types of common error. The first is random. A random error is, hey, I'm collecting data. Like I'm watching a seismograph, right? So I'm watching the rattle of the Earth's crust as it moves, and it's doing something like that. And somebody in the room sneezes. Okay, it's just a blip on my trace. If I look over a long enough period of time, that blip shows itself as being an anomaly, and I can either excise it, I can cut it out of my data set, or it will average to 0. Because randomness averages to 0 over enough observations. So this is something that I need to be aware of. Well, the numbers don't have to average to 0, but its effect will average to 0, right? If my real number is here, and there's somebody in the room that keeps sneezing, when I put all of that together, it still gives me the right trend. It just bumps it up a little bit. Okay. Okay, lots of data gets to be the solution to randomness. Here's the thing. I'm going to plot something against something else. Okay. And I find that I measure here, and then I measure there. Ooh, I'm fine. But then as I measure more, find the trend is that. So the more data you have, the more complete data that is, the less your errors are going to matter. Anybody done any statistics? What's the minimum amount of data points that you should take before you can even start thinking about spotting a trend?
Well, it of course depends on your study and the population you're studying. I would.
20 is a good number. 9 is an absolute minimum. You go from one table of statistical errors to another when you go from 9 to 20. Okay, the other types of error is systematic, which could be that you've designed your experiment wrong, or there's something wrong with the equipment. If your experiment requires you to take the mass of material over and over and over, and you're doing it on your bathroom scale, and your bathroom scale is not set to 0, then all your numbers are wrong. But that's a systematic error. The trend's still right. Every number is wrong. That's what systematic error is. All of the numbers are wrong, and they're all wrong in the same direction. We have a word for that. It's called bias. And that's why we'll run out of time, because I want to do this survey. I got a couple of examples of why humans are unreliable. And rather than try and squeeze those in today, we'll start with those on Wednesday, because that's another soft warm, fuzzy landing for